Alrighty, let's go over this. We want to find the square roots of these four numbers, right? So, a couple of these pretty easy. First one, the square root of 36 is just 6, right? Just take the square root and then you're done. What number, when multiplied by itself, gives us 36? That is the number 6. When we've got a fraction like so, just take the square root of the top and the square root of the bottom separately to get your answer, right? So the square root of 16 is, and then the square root of 9 is 3. And so, when we take the square root of this guy, we get 4 over 3. Just square root at the top, square root at the bottom, all is well. Now, when it comes to something like the square root of 24, okay, we have to do a little bit more effort. We have to break this down, right? 24 and then we write out our factors. So when we break this down, 2, and then these two are unpaired, so we put a 6 in there. So 2 radical 6, right? Finally, with number 4 down here, whenever you have the opportunity to simplify a fraction, right? 8 over 18 simplifies to 4 over 9, right? So just when you square root 4 over 9, you get 2/3. All right? Pretty simple, yeah? Let's move forward. What are we going to be doing today? We're going to find the ratio between the areas and perimeters of two similar figures. So what's happening with this is we're in a situation, maybe we don't know how to actually find area of something in general. I don't know, maybe we just haven't been given the right information. Maybe it's something that we actually can't find the area of directly for some reason. So we have to find another way, right? So basically the idea is going to be, we're going to go through and we're going to be given two things that are the same, except, one's bigger, one's smaller. Like similarity, right? We talked about similarity. So it's going to be two figures that are similar, and we're going to be given information about one of them, and we have to find out the information about the other one. All right? Does that make sense? So, as usual, I think generally speaking, the way the book does it, I guess it's fine, but oftentimes it doesn't lend itself to you being successful in every way that I want you to, okay? So I want, this is something that I do want you to know, because this is important, that if you know the scaling factor of two similar figures, then the ratio of the perimeters of those two similar figures is the same as the ratio of just the scaling factor, okay? The other thing you need to know is that if you know the scaling factor, you can find the ratio of the areas by taking that scaling factor and squaring it. So those are just facts. If you think about it, why is it the area a square of the scaling factor? It's because area is two-dimensional, right? So if you think about it, length is one-dimensional. So we're just comparing the two measurements that we see, and just whatever it is, right? That's why the scaling factor for two similar figures and the ratio of the perimeters is the same, because they're both one-dimensional measurements, right? But now when we get to area, is two-dimensional. That is to say, if we are taking a figure that's a similar figure and we're moving one from the small one to the big one, we're changing in two dimensions. We're changing length and width, but we're also changing, we're changing length, but that means we're also changing width, right? We're changing two things at the same time. So since we're changing two things at the same time, let me get out the way. Got it? Since we're changing two things at the same time, we're changing it, right, this way and this way. So the thing of it is, like if I'm scaling a figure up by 2, I'm scaling it by 2 this way, right? But I'm also scaling it by 2 that way. So I'm really taking the area and scaling it by 2 times 2. Do you all see what I'm saying? And if I were talking about volume, which this section doesn't go over volume, but there's one later on where it's going to basically, hey, remember we did this? Now volume. But volume, it's the exact same thing. You're scaling length, you're scaling width, and you're scaling height. So cubed, right? So the reason why I don't like the fact that, so they just sort of stop here. Like, okay, but like, how am I going to use this, right? That's the thing that I sort of don't like. So what I want to show you, I always make a little chart just to sort of get my information in order. And you can use this or you can not use it, but you're going to see I'm going to use this little chart that I make every time because it helps get myself together. All right, so, and I include volume here because eventually we're going to include volume here. Might as well get it here now. So, scaling factor, perimeter, each of them are one dimension. That's why it's just an X. Area, 2 dimensions. So instead of X, it's going to be X squared. And then volume, 3 dimensions, so we're talking X cubed. So let's say my scaling factor was, I don't know, 4. I had figured out my scaling factor. Well, now I know exactly what everything else is already, right? The scaling factor is 4. The perimeter is 4, because they're just the same, right? Well, if I want to find the area, what do I have to do? I have to square, right? 4 squared is 16. If I want to find the volume, I take the scaling factor and I cube it. 4 times 4 times 4, 64. See, now I have this whole chart here, and I don't have to think anymore. They're going to be like, all right, well, what's the scaling factor for the perimeter? What's the scaling factor for the area? Oh, it's right here. This is your work, and like 90% of the time, this is already basically your answer. You just have to sort of point to it. Hey, it's this one. But on top of that, if they have you do any sort of applications, instead of trying to juggle everything all in your head, you've done this out. Half of the work is already done. Now all you have to figure out is how to take these numbers and actually apply them to the problem. So again, is this like something I'm requiring of you? No, but I will be very honest with you. Every person I've ever showed this to that uses this chart does it right because they've got the information right here. They're not spending all this time letting their brain melt inside their head trying to do work all up here. All right. So I'm going to show you how I would use this whole chart thing in these upcoming problems. All right. So let's look and see how we do these. So look, and they give you a whole bunch of information. They actually tell you this, but they don't even need to tell you this because you've got the picture right here, right? So like they tell you, okay, 6/9, whatever. But like if you see, hey, this side is 6, this side is 9, ta-da, that same information is right there. So look at what they say. The trapezoids at the right are similar. And then what we want to know is, what's the ratio of the perimeters? What's the ratio of the areas? So they specifically tell you, hey, make it smaller to larger. That just means that the smaller number's on top and the larger number's on bottom, right? So look, we go through and say, all right, well, this one is 6, this one is 9. 6/9 is 2/3. So let me So the scaling factor is 2/3. Let me fill out the rest of this chart just so I have everything, right? This is just the same. This, you square it. This one, you cube it. All of my information is now here. So now all I have to do from here is just answer the question. So what's the ratio of the perimeters? Well, let's look. Perimeter, right here, 2/3. What's the ratio of the areas? Right here. 4/9. Ta-da! Right? By putting this chart on your paper, what you allow yourself to do is take all the information, dump it onto the paper, and then you can sort of let your mind be free. If you spend all of your time in your head, you're going to have problems. It is so much easier to take stuff with your hand and transfer the information to a piece of paper so that you're not trying to do 50,000 things up here. Can you imagine looking at that and go, so they give us 6/9. You know, I have to simplify that. Well, 6 and 9, they have a factor of 3. So what is that? Divide. I'm already lost. I speak for myself when I say this, that doing things in my head is like at least aggravating. Right? Like I would rather not do things in my head if I don't have to, because I know how my brain processes things, and I know for a fact if I'm sitting here just like thinking, it is going to take a whole month for that brain to crank its way through. But if I put it on the paper, suddenly, hey, my brain is free to process what's going on, because I'm not trying to, at the same time, hold on to all these facts and figures, because they're all on the paper now, right? And like, you're going to hear me say this basically every day from now until June, but it works. It makes a difference. It really does. All right? We doing okay in here? No questions? Okay, how about here? We doing all right? Make sense? Making sense, Donovan? Good, awesome. Cool. So now it's your turn. Now it's your turn. Give this one a try. They didn't give you a picture. All they've given you is a ratio. And they want you to tell them what's the ratio of the perimeters, or what's the ratio of the areas. Okay, so let's go over this. So first things first, we look at this and we say, all right, 5 to 7. They say larger to smaller, right? So we just want the larger number on top. So I'm just gonna, instead of doing 5 to 7, I'm gonna do that just so all of my ducks are in a row, you know? And then I'm gonna just fill it out. So 7 over 5, this would be 7 over 5. And then I'm gonna square it, so 49 over 25. And then what's this one? Good. Right? And doing something like this takes no time at all. Maybe you need a calculator for that last one, but like, yeah. That's an extra like second of punching a couple buttons. But now look, we can just answer the question, right? What's the ratio of the perimeters? This one. What's the ratio of the areas? That one. Ta-da! Okay. Pretty simple. Okay. So now what's the only thing that's different is now they're instead asking you to actually apply this information, right? Now we're no longer just, okay, well, what is the scaling factor? We're going to actually figure out, using that information, a quantity, right? So look at what they give us. They give us this picture. They tell us that the area of this smaller one is some amount. What's the area of the bigger one? So first things first, think about where we're going. We're going from the small one to the big one, right? We're expecting a larger number in return for our final answer than what they gave us. So we better have the big number on top, the little number on bottom, right? So we got the big number's 10, the little number's 4. Take the liberty of simplifying that right there, right? Scaling factor is 5 over 2. So the scaling factor was 5 over 2, and then we just fill it out just like we did before. The perimeter is the same. Area, we just square it. Volume, we cube it. All right, now we have all our information already again. So now let's go through. We're given the small area, we want to find the big area, right? Which of these are we going to use? Am I working with the scale of the figures? Am I working with the perimeters, the areas, or the volumes? Which is my final answer going to be? An area, right? 10 over 4, right? Simplify the fraction. 5 over 2. Does that make sense? For those of you here that can't see the chat, the question was, okay, well, 5/2, where did that come from? And it's, first of all, we know, again, we're working from the small one, the small area here, and we want to find the big area. So we know we're taking, of these two numbers, the bigger one, putting it on top. So 10 goes on top, 4 goes on bottom. and then it's just 10 over 4. Let's simplify it. 10 and 4 both have a factor of 2. We divide the top and the bottom by 2, we get 5 over 2. Okay? Cool. But so the question is, okay, so I've done all of this. I'm working with area. So which one of these am I going to use? How about the area one? Right? Now, just multiply and then we're good, right? Of course, I left my calculator over here. We're just gonna, we've got the small area. We want the big area. So we multiply by the area scaling factor. And I better get and my units are centimeters squared, right? Centimeters squared. So, and you know, you could do that by hand if you wanted to, but why? Especially if you've got a. But so, notice what we did. First, we figured out what the relevant ratio that we're given, in this case, the scaling factor of the sides, right? Put that where it goes. And then fill out the rest of the chart so that we have all of our information ready to go. And we said, all right, okay, we're trying to find an area, so we're using the area one, and then we just used it. Right? Your turn. The scale factor of two similar parallelograms is 3/4. The area of the larger one is 96 inches squared, and we want to know the area of the smaller one. All right, give this a try. Make sure you can do it. Alrighty. So one of the things I want to really, really impress on you: make your life easy. Don't try and do things the hard way. Make your choices so that what you're doing is easy. What do I mean? They give you the scaling factor of 3/4, right? You're going from the bigger one to the smaller one. Keep the smaller number on top. If your result is going to be smaller, make sure that the fraction you have is less than 1. Make sure that it's 3/4 instead of 4/3, right? So when we go through with this, leave it as 3/4. That way, all you have to do is multiply. Right? Because they tell you the bigger area is 96. So 96 times the area one, because we want to go from the big one to the small one, we've already got it written 9/16 so that it's easier to work with. We don't have to do no division. We don't have to do anything messy. Just times 9/16. And I'm also the type of person, I'm going to be like 96 divided by 16. Do that one first. Is that 6, right? 96 divided by 16 is 6. So this is really 6 times 9, or 54. And then again, our units squared, because we're dealing with area, right? Y'all see what I'm saying with this? I promise you, if you do things the easy way, you will process them better. Don't try and make mental gymnastics for yourself. It'll only frustrate you. And there's no reason to be frustrated when there's a better way. Here, now we're sort of application-y type problem. It's people are making a vegetable garden to donate vegetables to charity, which is wonderful. And they get some extra money, and they have the ability to obtain a larger plot of land on which to grow their vegetables. So they figure out that all the dimensions are 2.5 times bigger. They know last year they made 13 bushels of vegetables, and they want to know for next year, how many bushels of vegetables are they going to make? So we can figure that out because we know the scaling factor. Well, let's do it. So the scaling factor is 2.5. Now, I don't know about you, but when I try and square decimals, I get confused. So I'm going to rewrite this as 5/2. But, you know, it's the same thing, right? You prefer leaving it as a decimal and squaring this and having it be 6.25 or whatever? I will not stop you. Right, because this is in fact 6.25. But that's neither here nor there. The whole point is that we want to figure out vegetables. Which one of these is that? It's not, V stands for volume, not vegetables, right? So the thing of it is, even though we're talking about vegetables, what we're really talking about is area, right? We're talking about the area on which we have the ability to plant this food. So we are talking about area. So even though vegetables does start with a V, we are not using this one. We're using area. So we're going to go through and we're going to say, all right, well, last year did 13 bushels of vegetables. So let's figure out what our crop is going to maybe look like for this next year. 25/4, right? We're going from the small one to the big one, so we want our final answer to be bigger than what we had before, right? So 13 times 25 divided by 4, I want to say it's like 81 something. 13 times 25 divided by 4. Hey, I remembered something. $81.25 bushels of vegetables. Alrighty, so first things first. Again, they're sort of leaving this up to interpretation a little bit, but think about it. If you've got a piece of glass, if you've got like especially we're talking about a window glass. We're talking about price, right? So we should be thinking in terms of area. Yeah. If you just work with the scaling factor, especially if you're on the charging end of this, if you're the one selling this glass that you either made or are in charge of selling, now you're losing money if you're not using the right scaling factor here. And I'm sure in a few minutes I'll get into a really big long rant about charging what you're worth and stuff like that. So be prepared. It's coming. So The whole point is the glass, the smaller piece of glass costs $250. The bigger one is 3/5 bigger, right? We're trying to find the bigger one, so we want to make sure the taller number is on top. Taller number. The bigger number is on top. 5/3, right? And then the perimeter, same thing, 5/3. Area, we square those, 25 on top. 3 squared is 9 on bottom. For volume, it would be 125/27. And so now, once again, the whole point is that we need to identify, hey, we're working with a piece of glass that is growing bigger. The glass doesn't just grow bigger in one dimension, right? It grows bigger in both dimensions. So we have to charge for both dimensions, right? So this $2.50 piece of glass is now bigger by a factor of 25/9 for the area, right? Because we've grown it in one dimension and we've grown it in another dimension, right? So when we do this, what did I do again? There we go. And obviously you're probably doing this in a calculator. You come up with something like that, right? 6.54. Oh, 6.94. Look at me shortchanging myself. Repeating. Now, standard convention, of course, is since we are talking about dollars and cents, we cut off at the penny, and the 0.4 of a penny would round away. So we would say 6.94. But if you gave me 6.95 because you rounded up to the nearest penny because you're worth it, totally cool. I got you on that. So as long as you give me 6.94 or 6.95, $6.90 something cents, you know you good. But yeah, so one of the things, and this is a very common problem. This is a very common problem with just like being someone who works with your hands and makes things for a living, is how much do you charge? Right? And so I want to point out, depending on what you're doing, the difference is meaningful, right? If I had accidentally only charged by the scaling factor here, I'd only be charging something like $4. Think about that difference in the long term, right? It's a lot of money. That means you're cutting your revenue by like 2/3. You're only making 2/3 as much as you would. That's a lot of money if you're making $60,000 a year. 2/3 of that's only $40,000. That's $20,000 that you don't get because you didn't charge correctly. And that's just, we're talking about like two-dimensional things. Imagine if instead of making like stained glass or something like that, imagine you're sculpting. Or imagine you are carving or knitting or crocheting, right? Crocheting, especially when let's say you're making like a stuffed animal, right? You charge $5 for the little one. And if you're making one that's twice as big, remember, you're not just making it twice as big this way, right? You're also making it twice as big this way and this way. So if you've got a $5 bear and you make it twice as big 3 different ways, you best be charging $40 for that bigger bear, right? You all see what I'm saying? It's not just, here's this little thing right here. you're doing 8 times as much work, you better be charging 8 times as much. Imagine if you do 8 times as much work and only charge $10 for that. Not good, right? So be careful. Be very careful. Remember that your time is valuable, it has meaning, and you should make sure that you are compensating yourself for the work that you do appropriately. All right? All right, so last set. Here, they're giving you the areas, and we want to find the ratio of the perimeters. All right? So now we're like going the other way, right? So look, the bigger area is 98, the smaller area is 50. Let's simplify that. 98 over 50 simplifies, because both of them have a factor of 2, to 49 over 25, right? That's our area. Now, if I want to find the rest of these, well, look, I've got x squared, but I want x. So now instead of squaring, I'm going to square root it. Go the other way, right? So again, square root the top, square root the bottom. Square root of 49 is 7. Square root of 25 is, and then if we were to cube root all that, 343 over 125, right? Anyway, but like, now, what's the scale factor? Oh, look. What's the ratio of their perimeters? Oh, look. Right? Simple. It's just going the other way. But again, if you fill out that chart, it's going to mean that you have a lot less effort that you have to deal with, right? All right, here's your last practice problem. The areas of 2 similar rectangles are 1,875 and 135. What is the ratio of their perimeters? Okay, let's go ahead and go over this. So 1,875 over 135. Oof, right? This is where some shortcuts help. You see the last digit of both of these is 5, so we know we can divide both the top and the bottom by 5, right? We do that. And we just do the bottom. 27. And at this point, we look at that and go, okay, well, that's close to being like a perfect square. There's an extra 3 in there. Maybe we can pick something else outside of the top. 375. Is that a multiple of 3? Let's find out. 375 divided by 3. Oh, hey, it is. Perfect. So divide the top by 3, divide the bottom by 3. Hey, now that looks like something we can use. That's a perfect, well, not quite a perfect square, but it's at least kind of perfect squares on the bottom at least. So we go through. Well, let's square root the top and square root the bottom. 125 doesn't square root nicely, but it does simplify to 5 radical 5. The bottom, however, square roots very nicely. Square root of 9 is 3, right? And you can just leave it that way. that would be the ratio of their perimeters, right there. Right? And there we go.